Today we will start with our 10th lecture as it was missed in the last week. So I would also like to discuss how can we cover the last missed lecture. So we have two choices. One choice that we can conduct an extra 75 minutes class at your convenience. So you can tell me, I can also discuss which time will be more suitable. And next thing is that we could cover 75 minutes, let us say, in chunks of 3 classes, so that we cover approximately, let us say, 75. So we have 25 minutes extra rather than ending at 7:15 we end at 7:40. So these could be two ways. You can also give me your suggestions. Haji, हाँ जी मैर
सर
साहब.
यही ठीक है, हमने पहले भी एक दफा इसी तरह कवर किए थे, वो पता भी नहीं चला था और लेक्चर भी कवर हो गया था चंक्स में ना.
अच्छा ठीक है, तो फिर ये कि हमारे पास अब देखें आज पता नहीं होता है कि नहीं. Let us see. So we have 4 lectures. I don't know how many lectures will be conducted in the next week, because if Friday is Eid, and I think Thursday will be definitely holiday, but I don't know about Wednesday. So let us try to cover in these 4 lectures. This means that we will be covering 15 or 20 minutes extra. Let us say this lecture we cover 15 minutes extra, and in the next lectures we can cover 20 minutes extra. So this will be 60 plus 15, 75. All right. Let's try, see what can we do today. So here I will start with the recording. So today we will start with a very important concept, and that concept is related especially to the current state of the art 4G systems. And this system is actually also carried on to the 5G. So, but here we will try to understand the very basis of orthogonal frequency division multiplex or OFDM systems today. Now you can observe that in the last lectures we had studied single carrier systems. For example, we saw the famous 2G systems, and when those systems they are passed through a wideband channel, or you can say a frequency selective channel, where the bandwidth is much greater than the coherence bandwidth. So there you have intersymbol interferences. So we saw that how could we utilize that ISI to get if there is L delay path, so we can get L times diversity. So L time diversity can be taken in all the systems, may they be 2G systems or they be 3G systems. But other than that, the disadvantage was that one symbol will also have, for example, if L is equal to 12, then it will also have the previous 11 symbols interfering with this symbol because of intersymbol interference and all those delay paths. So we learned about that were done, especially the Viterbi algorithm in 3G, in 2G, and then the rake receiver in 3G. How can we take care of that ISI, and you can utilize the frequency diversity to give you L times gain. Now both those approaches you could observe that they were based on time domain view and 2 and 3G. Now here we will take a different approach. So Now we know one very important thing from our signal and system course. Adi, if you have an LTI system, then sinusoids are eigenfunctions. Now let us ask questions from some students to see. Acha, Aiza Ahmed, can you hear me? Aiza Ahmed? I think
Ji, sir.
cannot hear. Acha, good. Acha, Aiza Ahmed, do you remember from your previous courses of undergrad, what is an eigenfunction? Especially from signals and systems. Do you remember any type of eigenfunction, or what is the definition of an eigenfunction? Achha, no problem. Haji Umair Ahmed, can you tell me what is an eigenfunction?
सर ये सिग्नल्स को सर हमें आउटपुट को कैलकुलेट करने के लिए बेसिकली एलटीआई सिस्टम में यूज करते हैं.
नहीं, डेफिनेशन चाहिए मुझे. अच्छा, गुलाम मुस्तफा, can you tell me what is an eigenfunction? गुलाम मुस्तफा.
अस्सलाम वालेकुम.
वालेकुम सलाम रहमतुल्लाह.
सर आई थिंक ये दो सिग्नल जब 90 के एंगल पे हों, अगर एक की वैल्यू निकालेंगे, अगर उसका आइडेंटिटी मैट्रिक्स आ जाए तो वो दूसरा जो सिग्नल होगा वो 90 के एंगल पे होगा.
शाबाश, वेरी ठीक है, थैंक यू. शकूर अहमद, आप बताएं.
सर जब मुख्तलिफ डायमेंशंस में अगर हमने फॉर एग्जांपल उस मुख्तलिफ डायमेंशन में कोई फंक्शन को डिफाइन करना है तो उसके लिए जो हम ऑपरेटर या फंक्शन जो डिफाइन करते हैं वो आइगन फंक्शन कहलाता है.
चलें, ठीक है. हाँ जी, अवैस मक्का साहब.
सर एनी नॉन जीरो फंक्शन.
अच्छा, सही बहन. नॉन जीरो फंक्शन तो बहुत से फंक्शंस होते हैं. ऑल राइट, नो प्रॉब्लम. हाँ जी, सलमान साहब, वेयर आर यू? यू हैव रन अवे फ्रॉम द क्लास. ओनली 5 स्टूडेंट्स आर विजिबल. वेयर आर अदर स्टूडेंट्स? कितने पहुंची, इतने आप लोग के, इतने आप लोग शुक्र हैं तो ना. वो शुरू में स्टूडेंट्स आते ही नहीं है.
अभी सर आए थे, मेरे ख्याल में फिर शायद लीव कर गए.
सर जीरो लगाएं साहब.
जो है उनको तो लगाने देना मार्क्स, आप लोगों को तो मार्क्स लगाने दें. देखते हैं वो यार, हर की वजह होती कहते ऐसे ऐसे. चले, आप लोग तो माशाल्लाह आए ना. अच्छा, remember that eigenfunction is actually that function when it is fed into an LTI system, the output is also of the same form as of the eigenfunction. This is the exact definition. For example, what was the famous eigenfunction that you have learned? What Ej omega t. You remember Ej omega t? If input to a function is Ej omega t, what is the output? Output is the same form as Ej omega t, but multiplied with the constant which is you write at h bracket Ej omega t. Do you remember in signal system? Yeah. Why we use Ej omega t? Why Fourier transform, discrete Fourier transform, inverse Fourier transform, all those transforms are of form Ej omega t. Ej omega n is just a discrete version. Basic thing is Ej omega t. Do you remember now? Fourier series, Fourier transform, discrete Fourier transform, discrete time Fourier transform, fast Fourier transform. So all these transforms, they are based on using the eigenfunction Ej omega t. So Ej omega t is very important. If you feed it to an LTI system, the output is of the same form as of the input, just multiplied by a constant that is dependent on the input, which is h of Ej omega t. This is a very important definition of eigenfunctions. But remember, in signal systems, when we were studying signal systems, there the eigenfunctions were actually for LTI systems. LTI means linear time invariant, invariant. So they are not changing. And there we have studied what you can revise in your from your previous book of signal systems. Now, what is the problem? Here we know that yes, ISI occurs in a single carrier system. Transmitted signals are not sinusoids. So remember, is there any difference between eigenfunction and sinusoids? Actually, they are the same, because you know Ej omega t is cos plus j sine. So cos and sine are just sinusoids, just shifted by pi by 2. One is along the real and another is along the imaginary. So they are, you know, sinusoids or eigenfunctions or Ej omega t, they're the same. Now ISI is occurring in single carrier system because transmitted signals were not sinusoids. Okay, so you were not sending a sinusoid signal. For example, you could be sending a pulse, a PAM, a BPSK signal, any type of pulse. For example, a sync pulse, a duo-binary pulse. Thousands of pulses are there in communication. Yes, so for sake of simplicity, we know why do we send those pulses, but just you are not sending, you know, a full sine or a cos. You are sending those pulses or signals. They were not sinusoids. Actually, we can never send a sinusoid. Ej omega t cannot be sent through a channel. You know what is Ej omega t, sin omega t, cos omega t? So what is cos omega t? Means cos omega t going from infinity to infinity. I cannot send this signal through my system. I cannot afford. My signals are always for short durations. Now, so we have a problem now. We have this property, but we cannot utilize this property here, especially in single carrier system. Now, what should we do? Have you understood what is single carrier system? वो जो अच्छा ये पूछते हैं किसी को आता ही नहीं. हाँ, ये सिंगल कैरियर सिस्टम सबको आता है कि नहीं आता? हाँ, सलमान यूसुफ साहब. Can you hear me, Salman?
जी सर. जी सर.
Why did you went away when I was asking question?
सर मैं असल में इस टाइम ड्राइव कर रहा हूँ, मैं मोबाइल पे कनेक्टेड हूँ.
So how can you talk? It's very. Are you using some device on your ears? You are driving a car as well as listening.
सर अभी तो मैं खड़ा हूँ ट्रैफिक में, तो मैंने दोबारा कनेक्ट किया इंटरनेट.
ओह अच्छा अच्छा. सही है. All right. अच्छा, can you tell me? Do you remember single carrier systems? What is a single carrier system?
सर जिसमें हमारा कैरियर एक होता है, मॉड्यूलेशन उस कैरियर के ऊपर हुई होती है. सिंगल कैरियर पर चैनल यूजुअली बोलते हैं CPC.
हाँ ठीक कह रहे हैं. So we studied two systems, 2G and 3G. Which one of them was single carrier?
2G तो सर फॉर श्योर सिंगल कैरियर है. 3G का सर मुझे श्योर नहीं.
Yes, you're right. Yes, good. Yes, 2G is definitely a single carrier system, no doubt. Even in 3G. Okay. So actually we were studying 3G, pseudo noise and all that, but we were just studying it at the baseband level. All right. But remember that the signal has to pass through the passband. We just study, equivalent baseband channel representation, chapter 2, if you remember. We were studying equivalent baseband representation of the channel. But actually, channel has to pass. And how does the channel pass? Channel has to pass. Yes, in that case, the channel actually is passed by the notion of spreading the signal over a very wide band. So that is why it becomes a wide band signal. That pseudo noise chip and all that which is used. So should we call it a single carrier? It's a very good question. Actually, I am also confused. CDMA system should be called a single carrier. They are wideband systems, no doubt, but are they wideband on a single carrier, or their pseudo noise sequence is not on a single carrier?
सिंगल कैरियर होगा तो वो सिंगल कैरियर सिस्टम ही कहलाएगा। जब उसको स्प्रेड भी करेंगे तो कैरियर सिंगल ही रहेगा।
For carrier we need that cos omega and sin omega to shift, but there we have this pseudo noise sequence. So let us this question we won't touch here at this point of time, because now I am also having confusions here. But single carrier is very simple, as you have studied there, that you just multiply. If you have I and Q channels, you multiply with sine and cos, or you just multiply with cos. So you have that basis of cos or sine and cos omega t, so you are on a single carrier omega. But in pseudo noise case, you are actually spreading the signal of that over W bandwidth by that. But I think you are right, because that is spreaded, I think, in the baseband level. Again, this baseband signal has to be transferred to the passband, and that can only be done if we modulate that pseudo noise onto the carrier. But this will become apparent in the chapter 4 when we'll be studying. So, all right, good. Your answer is almost correct. Thank you. So, I come back to the lecture here. So, in a way, I think you can say here 2G is definitely, but I think 3G should also be coming in a single carrier system. Now, second, if the channel is underspread, now this we have learned many times. What is underspread? Coherence time is much larger than delay spread, and we have saw many times, chapter 2 and also in this chapter. Coherence time is of the milliseconds and delay spread is of microseconds. So we can say that for that much coherence time, the channel is coherent. The channel is not changing sufficiently, so we can say the channel is almost invariant or time invariant. Now, under these circumstances, we can say that we now go from time domain to frequency domain. Not time domain view, but frequency domain view for these frequency selective channels. This is the basic idea of using the frequency domain rather than the time domain. Let us try to implement this frequency domain over our time domain model. Now, you all know this is the famous frequency selective model, which we have been learning many times. So L, they were the number of taps, L is equal to from 0 to L minus 1, or L are total number of taps at L. This we have also seen that L is equal to TDW, or delay time is equal to L over W. This can also be proven from chapter 2 knowledge. So this is also seen previously. Now again we are saying that the channel is invariant for that coherent time. So this means H coefficients are not changing with M. So they are actually constant with respect to M. So what is this M? H of tau. Sorry, this is not tau. This is H of t, X of t minus tau, and this is Y of t. So actually this should be H of tau, X of t minus tau. This is actually H of tau. L is your tau, but here it is M because it is now tau and t. But now it is no more function of t because it is invariant. So this will become H of L. This will be H of tau, L is tau, X of t minus tau, in the convolution, and this is t, and this is t. All right. So this is your simple convolution for an LTI system. Now this is right. We have learned this previously, no problem. Now, how can I use my eigenfunctions? But I know eigenfunctions for LTI, they were out of infinite duration. I cannot use them here. My signals are not of infinite duration. My signals are of finite duration. Let us say NC symbols. So once they are finite, they no longer remain eigenfunctions. So how can I make them an eigenfunctions? So what I do a trick, and that trick is that I use my cyclic prefix to the symbols. For example, let us say my symbols are going from 0 to NC minus 1. So what I will do, I will put a cyclic or the same signal, okay, before this signal So that it looks like a periodic signal or a cycle. So before D0, again I will repeat NC minus 1. Then before NC minus 1 you will have, in a way you can say, NC minus 2. So that will come before NC minus 1, minus 2, and so on and so forth until you will go till NC minus L plus 1. Now, so I tried to understand this from the book notation and it became difficult. So I said that if I am having difficulty, I must make it easier for students to understand, so they can understand how can we convert this D block, which is the actual data signal, okay, to this X block, which is actually the cyclic version or the same data symbol but added with the cyclic prefix. Prefix means before. So here, this is an explanation here. Let us say, before we take L is equal to 3, let us just try to understand. So you can see that my data is going from D0 to NC minus 1. So total symbols we know are NC symbols, which were originally, NC minus 1, minus 0, NC minus 1, plus 1. So we have NC symbols here, no problem. Right? No problem. Now what I repeat here, this will be NC minus 1. This will be NC minus 1, minus 1. But how many things should I repeat? That is a very big question. So the book answers that this should be total L minus 1. So if I say that L is equal to 3, in that case this must be equal to 2. So I will put 2 more symbols, which are cyclic version of this and from here to here. Their repetition of these and symbols, they will be coming here. Alright, this is like this. This will become NC, this will become NC minus 2. So total number of symbols will be NC plus 2, or you can say NC plus L minus 1. Alright, in this way you can see it like this. So now what is written in book? In book it says no, it goes to NC minus L plus 1. In book it says it is going to NC minus L plus 1. Alright, no problem. We say alright, NC minus L. But what is L? L is 3. So minus 3 plus 1 is minus 2. It is going to NC minus 2. And same is which I have told you, NC minus 2. So we will go from NC minus 1 to N, because we will go to L minus 1. Now why this L minus 1? Why this is so important? So to get rid of ISI. Get rid of ISI. Because remember, before this block, like the symbol before this, okay, will have L delay paths. So it will come at its time and then it will have its L minus 1, the remaining delay paths. So they will be just replicas. So meaning that in these two symbols, you will be getting replicas of the previous symbol. That is why L minus 1. Notations of the book you can use, no problem. Just I was trying to make you understand all of this notation in the book. So create, NC plus L minus 1. L minus 1 symbols, the repetition of the previous are just put before. So again, we add a prefix before L minus 1, consisting of data symbols rotated cyclically. Okay. So again, this is the output, and again, yes, the output is going from 1 to NC plus L. So now because X is now large, right? So for every shift of X, right, because now I will be having my X, which is actually the size of NC plus L minus 1. All right. So NC plus L minus 1, that is now being convolved with H. All right, which is size of L. All right. So you can understand that what will happen with their convolution. So we find how many symbols? 1, 2, NC plus L minus 1. Remember here that the data block is NC plus L minus 1. So we first of all say, all right, we just find the output for time 1 to NC plus L minus 1. So I put 1, so I get Y1. All right. For 1, I put M is equal to 1. So this will be X of 1 minus L. Then this will be X of 1 minus 2. All right. So this will be Y of 1 will be equal to X of 1 minus L W1. W1 Y1 is constant. Now X of 1 minus L. L is 0. This will be X of 1 minus 0. This will be X of 1. All right. H of L will go with X of L. Then L is equal to 1. This will be X of 1 minus 1. This will be X of 0. All right. But as you know, my data symbols, this length is going from 1 to NC plus L minus 1. So that will not exist. The next you have 1 minus 2. So 1 minus 2 is minus 1. Minus 1 will also not exist. Right? So the output will just be given by the first. This way you can just extend that. All right. So for the last, when we have NC plus M is equal to NC plus L minus 1, NC plus L minus 1. So L0, this will be same. But for L minus 1, this will be NC plus L minus 1 minus L plus 1. You can see minus L cancels with plus L, plus 1 cancels with minus. So you will have NC. So here you will have NC. All right. X of N. But you can just check by just putting the value. You can do it just I was explaining. Now we have two considerations. First of all, we know ISI will extend over the first L minus 1 symbols. All right. So what does the receiver say? All right, I will ignore the first L minus 1 symbol. So the first L minus 1 that were actually added. You can see here. The first L minus 1 symbols that will be actually added here, they will be ignored by the receiver. So it will start from L. So L minus 1 is ignored. So Lth. So 1 to L minus 1 is ignored. So we start from L. And you will go up to NC plus L minus 1. All right. So now this type, because of this cyclic prefix, we can give the output. Now, remember now, what will happen to the output? Haji. So what is the length of the input? And input will be NC plus L minus 1 minus L. This will be a plus 1. So minus L can, yeah, I have also done this here, so there's no difficulty. Maybe I am yes, here. So first L minus 1 are ignored, or first two symbols will be ignored. So you look for DL from after L minus 1 to DNC plus L minus 1, or you will look from D0 to DNC minus 1. So what are the total symbols? Total symbols will be NC minus 1 minus 0 plus 1. NC, or in other words, you can say NC plus L minus 1 minus L plus 1. So minus L cancel. Minus 1. Yeah, this is minus L cancel with L, and plus 1 you have to do. So to include the first symbol. So you can see this will be again NC symbol. So we will be just now looking over NC symbols. Because we have ignored. So because of that, you can see that my output can now be represented as, first of all, the output has changed. Now it is just, we are just taking the output from L to NC plus L minus 1 over, only over the length NC. All right. And so we are just considering D because all of the remaining symbols, they have been removed. Okay. And because of this cyclic condition, because you know previous symbols, once you are, shifting, once you are shifting, all right. So what will be coming before, as you are shifting forward, before you will be getting the cyclic version, because you have the cyclic prefix here. ठीक है ना, जैसे कि लीनियर कॉन्वोल्यूशन में क्या होगा भाई, देखिए ना, दो सीक्वेंसेस आपने दोनों को खड़ा किया, अब क्या होगा कि जी एक दोनों खड़ी थी, एक को आपने उल्टा कर दी माइनस टॉप, और फिर प्लस टी के हिसाब से उसको आपने शिफ्ट करना शुरू कर दिया, डिले या लैग जो भी एडवांस, यू नो मोर देन मी, सही है. बट once it has passed through, convolution is ended. But here what happens that it is not just passing through, it is actually passing through with its cyclic copy. So that cyclic copy is actually called, the famous cyclic, yes, circular convolution. Remember, if you remember your digital signal processing course of undergrad, so this, circular convolution, this is used actually for DFT sequences. So we know that convolution in time is equal to multiplication in frequency, but convolution in time, if I want to take its DFT, this will be circular convolution in time will correspond to product of the DFTs in frequency. Very famous rule. You can also get good practice. So figure 3.21. Alright, we will also see those figures. 3.21 also figure and this 3.20. So let us see them. First, let us see this 3.20 figure. So don't be confused with this D0 dash and IDFT. We have not discussed. Just simple think that we have these symbols. D0, Dn minus 1. This is wrong. This should be NC. Alright. So we have NC symbols. We just add a cyclic prefix. Okay. And we know the cycle will be L minus 1 and just send the data. This is a transmitter. Send the data through the channel. So this is what we have learned here. Now, how it is passed to the channel, we saw it is actually a type of circular convolution. So, in exams or in your previous course, we have learned in digital signal processing how this is done. This is as follows. Let us say I keep one stationary, so 0 is stationary. This is H0 to HL minus 1. All other values of H are just 0 because H is small, H is just L length. And NC is quite large. You will see in a while, NC is quite large. So we will say H is length of NC, but all other those values of H which are not occupied by L H0 to L minus 1, they will be substituted with zeros. All right. So now you will put the value of your X and you will start first multiply these are zeros, multiply this by this and add up, you will have the convolution. Then you will shift this one circular shift. One shift, this will go here, this will go here, this is this, like this. And again multiplication, you will get an output. In this way you can get an output. This is a small way. In this way you're very easy. You are just moving in circles and you are getting an output. So if you try its equivalent in linear convolution, then you will have to make its replicas and then convolve with the replicas. So this is more easier approach. So use in famous, digital signal processing of Oppenheim and all that is given there. So you can also get a good revision of circular convolution. So you see the output will be going from is of NC length from L to this thing. And we know it is of only L length, but we have to put more zeros. Add zeros, so that is length become NC. Now we can write our previous equation by the famous representation of Fourier convolution. Achha, I have also done this thing so that again students will become confused. Sir, your value kaise aa gayi? Hai na? This value. I also thought that how can we say this is this and this? How? So I said, all right, no problem. Let us do. So I tried to solve this equation because many students will not remember how to take modulo. So the modulo is a very important operation, especially for computer science persons. But now because of digital systems, it's also taken root mathematical operation in case of digital communication systems. So how this is applied? Let us try to see. Let us say yes, all this L to NC. So let us say I try to find at ym, m is equal to L, capital L, m is equal to capital L. I put L minus, this is capital L minus L, this is, L is moving like this. So L can, this is minus L modulo NC. I have deliberately taken this so that, and also book has given this figure. You understand, minus modulo. So no problem once it comes in exam. So I just open this up. This will be L0 D minus 0 modulo. So what is, what is modulo means? Remainder. If you divide 0 by NC, what is the remainder? That is modulo NC. So if you divide 0 by NC, you will get a 0. So no problem, no use of taking modulo here. It will be just D0. Here this is difficult. So next step, you have L is equal to 1. So you have to put minus 1. So take minus 1 modulo NC. That I will tell you how to take it. Then you have, because I took an example where L is equal to 3. So you'll go from 0 to 3 only. 0 to 2, sorry, L minus 1, 2. So minus 2 modulo. How can I take minus 2 modulo? Let us check. So first of all, let us just give an example. Let us say NC is equal to 10. Assume NC is L is equal to 3, but NC is 10. What is minus 1 modulo 10? So I will say, how can I, first I will take, what is the multiplicand by which I can divide? I will say, alright, minus 1 into 10. This is minus 10. Alright. But I want to get minus 1. So the remainder is actually 9. So I will add plus 9. Once I add plus 9, so 9 is the answer of my minus 1 modulo 10 equation. Alright. Similarly, here you can see, if I say minus 1 mod NC, so I have alright minus 1 NC. So but what should be, because minus NC will be minus NC, but what should be added here so that I can get minus? So NC cancels and I'll be getting minus 1. This means NC minus, ये थोड़ा सा मुझसे ना ये notation गलत हो गई, इसको इससे लिखें. अभी is equal to जाएगा. This is not the right way to write it. I should have used computer science notation. So this is actually, we are taking mod. This should be mod of this whole. So mod of this whole is just the remainder. Okay. For example, let us say, what is the 7 mod 5? It is 2. Because if you divide 7 by 5, so 5 ones are, but 2 is the remainder. So 2 is the output. What is 10 remainder 5? You will say it is 0 because 5 completely multiplies 10 and 0 is the remainder. Alright. So here, because of minus, this is a problem. That is why I have just deliberately do that so that you have no problem. So you can see H0, D0, H with D. H will go with NC minus 1 and this will go with NC minus 2. And you can check here with this D0 N minus 1 because wrong in book should be NC and then NC minus 2. Here is not shown, but this will be NC minus 2 and so on and so forth. I hope you are understanding this mod operation, very famous operation. Achha. So, so what is W? W is again like Y of NC length, right? Right. So everything is NC, 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 NC. Right. Cyclic convolution. All right, cyclic convolution. But then मुझे याद था circular convolution, but maybe it is called cyclic convolution. But you can correct from your book. Now another thing. All right, this is convolution, no problem. But what is its convolution in Fourier? But because this is cyclic convolution, I have to do its Fourier in discrete Fourier transform. Right? Because discrete Fourier transform matches with cyclic or circular convolution, whatever the name, you can check from your DSP books. So I take the Fourier of H or of DM, both I take Fourier. So this is the Fourier. Achha, many students will get confused because there are many transforms, DTFT, DFT, Fourier. So I've just done this for your understanding here. So you can understanding, and once you don't get confused with these digital and analog signals. So basic is EJ omega t. So once I sample it, it becomes MT. Alright. Now what is T? T is the sampling time. But sampling time is equal to 1 over Fs. So Fs is the sampling frequency. Now F over Fs is actually digital frequency. Now this becomes EJWM of the famous, discrete time Fourier transform, where x of Fourier transform is x of n into e minus j omega n in your previous course. But let us say it is e minus j omega m here, so that we can differentiate between n and m. All right. Now this is like this. Now what happens here? Here this happens that this in discrete Fourier transform, what actually happens? So we also discretize the frequency. Okay. So how we do that? We say that our basic frequency is 1 over nc. All right. The digital frequency is 1 over nc, where c, nc is a block length, so 1 over nc, and times n. So for that every n you will be getting the transform. This transform will correspond to the frequency actually fd, which is actually n over nc. So as n is changing, you will be getting the different Fourier transforms at those different frequencies. They are now represented at actually n over n. What is n over n? N over nc is nothing but multiple of 1 over nc. All right. So this is the famous DFT. Now we go to the book. So, don't go get confused 1 over under root n. Don't get confused. Remember, this 1 over n has to come. Either you put it in the Fourier transform or you put it in the inverse Fourier transform. Because 1 over t or no 1 over t. All right. So 1 over 2 pi, if this is omega, but for these signals, so it depends. So it is 1 over n, but here he has put under root, no problem, under root. So that will actually become n or nc. So don't get confused here. So this is our DFT, famous, very famous. So what I do, so similarly I will have Fourier transform for h. So I take this equation and I take Fourier transform on both the sides. So Fourier transform of this will be Fourier transform of the circular convolution is equal to product of the Fourier transforms of each h and d. All right. So don't get confused with these NCs because they are part and parcel. You have to put NC somewhere here in any of the transforms. Book has used this, he has used this notation, no problem. This product, all right. We can write 3.133. So you can see that 3.133 was actually y. This was all in. This was actually time, right? All time. L was the L and CL. They were all just different times. So already in time. So I can take its total. कहते हैं उसको Fourier DFT, but DFT you have to take. So this will become y tilde. This will become product of h tilde plus w tilde. So I can write this as this thing. Okay. Yes, this is a vector, but he has just written it as each every coefficient. So remember, it is just the product. But here, once you take the convolution, it will be just the product of DFT of this and DFT. DFT at one frequency will just multiply DFT at other frequency. DFT at that W will give DFT at that frequency of Y. Simple. That is why we can write it as every n is dependent on that Hn and that Dn, which actually comes from this Dn or that Hn from the Fourier transform or from the DFT. All right. I hope everyone is understanding. This is no problem. Hn comes from here. L tap H multiplied by N. So he is actually multiplied by NC before. That is why that 1 over under root NC is cancelled. Rest you can see this is just the same as this thing. Dn and Hn formula is actually the same. There the coefficients are different, but the formula is the same. You can see. Here it was Dm, here it is Hn, no problem. Because Fourier's channel coefficients were going from L0 to L minus 1. That is why we took its Fourier from L to L. And yes, so what is the nth component? Nth component will represent the channel at this frequency. If you talk in terms of omega, that will be 2 pi N and C, but if you talk in terms of F, so that will be N over NC. All right, N over NC, like this. Achha, he has written this W, but actually he has not discussed W at this point of time. Maybe we should discuss here. W is actually the bandwidth. We should have discussed rather than just putting here and making everyone confused. Here. Oh yes, oh sorry, good. So we have found this W, all right? This W is here, all right? So I hope you remember this W. So this was the same W that we saw there in our previous, TD is equal to L over W, right? So coming back here. So remember that N over NC are just ratios. N over NC is NC is a number, block size, and N is also an integer. But if you want to write this in terms of right, because here it was actually converted. I told you that what is happening here, we actually converted. Once you do is digital, this digital is what is a ratio, F over F. You already have converted this ratio. All right, this is actually number. Okay, hertz they have actually cancelled. So okay, so yes, if you want to write this in, you have to multiply this some frequency. That is why he has multiplied this with W, right? So actually W chapter 2, you will see W is actually there it was actually the baseband, but here this W would be actually the wideband, the channel pass band bandwidth that has been allocated to the to the system or whatever. Now similarly we can write all of this thing, which we first write in circular convolution, then we write this in DFTs, and similarly we can also write this in terms of matrices. All right, no problem. In terms of matrices, convolution circular is written as CD, where C is the famous circulant matrix. So you could see here. So again, this is the same, H0. All right, first, then all those zeros which are padded, and then L minus 1, L minus 2, H1. So in the second row, you will just shift it towards the right. So this H0 will come, but this H1 will come here because it's a circulant matrix. Again, everything is following the circular, क्या कहते हैं इसको, circular convolution. Okay? So next will be this whole shifted here, but this H2 will come here. So this will go on until again this H1 L minus 1 will come finally here, and this will be shifted here. All right. So you can see that this is, after this you will get this, because after this will shift here, and this H0 will come here. So you can see all of them are actually cyclic shifts of one another. So U is equal to the famous CD, and in this way you can, because this is circular convolution. All right. So you've just written the circular convolution in terms of a matrix. So now I take the Fourier of this matrix. So there is another approach of taking DFT. One DFT you have seen, but another thing is that you can use the famous matrix. This is a U matrix, okay, which is size is NC, and each of its coefficients is like this. The same thing, EJ 2 pi. Instead of NM, it here written KN. No problem. KN, no problem. And NC block, same thing, 1 over 100 NC. So now in this we are doing with this the same thing with the help of matrices. So in matrices, all these terms, this is also explained in, in digital signal book, because, all of the operations now are being done through matrices. So all of these transforms are being done through by matrices. That is why this is used. So what we have done actually, U is equal to CD multiplying with U. So we have multiplied, when you multiply with U, this becomes like this. So when you multiply with U, this U goes here, but U with, you will see in a while how this happens. U with C actually gives you a eigen, or the eigen matrix, or the diagonal matrix, which we are only interested in the diagonal. Yes, and diagonal entries are actually, they are actually equal to the coefficients, the Fourier coefficients of H. You can see, what is UH? UH is actually the Fourier of, UH is the Fourier, is the matrix of EJs. UH, this becomes the Fourier. All right. So this is a, NC cross 1 vector. So I take, first will be the first diagonal entry. Second, n is equal to 1 is will be second diagonal entry. In this way, all the diagonal of NC cross NC will have these terms, the Fourier transform of H. So they have to come here so that you can multiply and then you will get the right answer. Otherwise, you won't be able to solve the metric sizes. This is the rule. Now, if you compare this equation with this equation, so again, this was a little bit tricky. So I did here. Yes, this is one equation. This is second equation. All right, which you saw here. Fourier of this gives eigenmatrix. Now you have to write an eigenmatrix, otherwise it won't be multiplied. So DFT of U, this is U capital U, NC cross NC. This is U, is NC cross 1. This gives me NC cross 1. And yes, this is the size of UU, which is this is NC cross 1. This will also be NC cross 1. This is NC cross NC. This is NC cross 1. This will be NC cross 1. So again, this is NC cross 1, you can see, and this NC cross will be placed along the line. This is deliberately done so that you can get the correct output. Now, if you compare this equation A with conversion, so what is this equation A? U is equal to CD. All right, I take U on board, but this is U vector. I take capital U, which is matrix, to make it in the Fourier transform, UCD. Now we know from B that UU is equal to lambda UD. So I equate lambda UD with UCT. UCT is equal to lambda UD. And this U is capital and this U is also capital. So I can post multiply DD goes away. Again, the UC has to be equal to lambda U. In other words, C is equal to, I post multiply, pre-multiply with U minus 1, U minus 1. So C is equal to U minus 1 matrix U. So this we have proven. Now, so what is our Y? You can see my Y was actually, circular convolution. Okay. Or I could write this as matrix form, C with D. C is a circular matrix. Or I can also say C is equal to this thing, so I can put this value. This is the time domain expression of my output. This is very valid. Same he has shown here. Now he gives this figure. So how the OFDM system is actually designed? It is actually designed based on this equation, right? So what we do here, this he has explained, so I will also explain here. So what we do, so first of all, what we do, we take the actual, these are the actual data symbols, all right, my 1 0 1 1 minus whatever, they are taken here. So I take, these are the symbols I take, okay, my symbols. and I take their IDTFT. I take their inverse, which means I multiply with u minus 1. And then I get my D vector. The D vector which you actually started with is actually found from the inverse of the data symbols. Inverse of the data symbol. So just for your sake of information, today the class will go up to 7:30. All right. So we have 7:30 or 7:35. All right, 7:35. Nee, 7:30. 20, 20, 40, 60. We will see. 15 minutes or 20 minutes. So if we distribute in 3 lectures, then we will need 25 minutes per lecture more. So we will see. All right, let us see what can be done. Acha. So what I was saying? Yes, these are the actual data symbols. All right. Now I take their inverse DTFT, so I will get. So I actually these data symbols are in the frequency domain. So I say this data symbol is one frequency, this is another frequency. They are on different frequencies. Then I take their IDTFT. So I convert them into time domain. This is a time domain signal D0, D1. This time domain signal D0, D1 is actually here. This is a time domain signal. All right. Okay. So I add my SIC prefix. I pass it to the channel. So channel gives me this output. Okay. I remove the prefix. The prefix that was added here. So I will remove that prefix. All right. And then I take again the DFT. So I've already taken IDFT. So once I take DFT of my IDFT, I will get back my dashes. But there will be the received symbols. Why? This is what is actually happening. Here's a trick. You take inverse of the transmitter and you take Fourier, not inverse, but Fourier at the receiver. This is the trick. Now let us see how this trick is working. Again, he has not explained. Again, I explained this in my lecture so everyone understands here. You know what is happening? D is actually U. If you take UD, this becomes Fourier. But if you U inverse, this becomes inverse Fourier. So, I just replaced my D by inverse Fourier because D is actually inverse Fourier of D tilde, which is versus the actual symbols. Actual symbols, your frequency modulated, your carriers, and so I take its inverse. So actually, you can see here what this is written. Data symbols in the frequency domain are related through IDFT. These are data symbols which are actually, on the transferred on the carriers, and then I take their inverse. So how can I take IDFT? I have to the signal in frequency domain. This D signal is in the frequency domain. All of these symbols, one symbol will go with one carrier, other symbol will go with second carrier, other symbol will go with third carrier. So I have carriers, which you will see how to make these carriers. Okay, not one carrier, single carrier. This is not single carrier. This is multiple carrier. FDMA is 100% multiple carriers. This is OFDM. You have multiple carriers. Each carrier will take one data symbol. So I have total of NC carriers. All right. So this is signal in frequency. This is Fourier transform. यहाँ कितने carriers हर carrier की amplitude. This is Fourier transform. I take it. So IDFT. I make it time domain. This is my time domain signal. So my time domain signal D was actually the inverse Fourier of the Fourier signal. So you can see this UU cancel. So you have actually U minus 1. This D plus W. Now at the receiver, I must take the DFT. So I must multiply with U. So UU cancel with U minus 1. And you are left with delta D, UY and UW. But what is UY? UY is the Fourier of Y. Yes, I want Fourier of Y because the receive symbol is actually, it has to be the Fourier. Because send signal was Fourier. Noise also has to be Fourier. Yes, I take UWY. Here this is lambda D. But what is lambda D dash? But you know that D dash was actually the actual Fourier signal. And what is tilde? What is tilde? You saw here. What is tilde? Tilde was, what tilde was these symbols. All are zeros. There are symbols on the eigenmatrix which are what? Which is UH. With Fourier of H. Everything is covered here now. So the final symbol that you are getting are actually the output that corresponds to the actual input Dn, yes, with some change, all right. But for every other carrier, you will have n different. So all the carriers are independent, and you are getting these independent. हमारे अब्बू दादा बुला रहे हैं आपको जाने. So you get it. So
Sir,
you
एक
know,
question
noise
है.
was also UW, but you know, noise is, yeah, we have learned isotropic and all that. It's CN will remain this one. It's never change. Yes, yes.
सर इसमें जो हमने मल्टी
you can
कैरियर्स
ask.
का आईडीएफटी लिया है सर, उसके बाद वो
answer
टाइम
पूछें.
डोमेन में आ गए. सर जो हमने टाइम डोमेन
Yes.
बना लिया है सिग्नल्स का, उसको बाद में हम ऐड करके चैनल्स में भेजते हैं, क्योंकि चैनल्स में वो सारे पैरेलल शो हुए हैं ऊपर. तो इसका मतलब है कि इतने ज्यादा सिग्नल्स जो होते हैं वो चैनल में जा रहे होते हैं, मल्टीपल जितने हमारे कैरियर्स होते हैं, या सिंगल वेव जा रही होती है.
Yes, देखिए ना, what all of them, they are actually one symbol. देखिए ना, once you take IDFT, all right. So what will happen? You know, in IDFT you have n input, you get n output. Okay? In DFT the beauty is that n input, n output, n input, n output. So you will be getting n output here. All right, but you can see that the carrier thing is actually inherent. It has actually been मतलब के क्या कहते हैं इसको, mixed here. All right, because you can see that how do you make this D0? This D0 is actually made from all of these. है ना भाई? Inverse में क्या होता है? Inverse, you take inverse. What is inverse? X of f e minus you know jft or j2 pi ft. So you take all of these are making this D0. All of them are having all of these things in them, and then they are being sent. All right, so they are being sent with, you know, with time. This is time, 0, time. They are sent with time. First symbol, second symbol, like a, you know, cyclic prefix, like a, you know, block data. They are going like a channel. All right. So, but that inherent frequency is actually all the frequencies are covered inside this D0, and they are going in a timely fashion in a block mode. So you can see this figure. The data symbols actually, they modulate the subcarriers, NC subcarriers. So NC subcarriers, they actually occupy the total W bandwidth, and all these subcarriers, they will be separated by W over NC. So I have told you today you will go up till at least, let us say when the lecture is complete, so we will go up till 7:30 so that we can cover the previous lecture. So they will be separated by W over NC. Now the data symbols are then converted through I to time domain signal. So time domain X0, D0, D1, D2, D2, or whatever, DL, NC plus L. Then you put cyclic to get rid of ISI. So you send receiver ignores cyclic, converts NC symbols back to time domain through DFT. You get back the original signal. So the data symbols on the sub are maintained to be orthogonal as they propagate the channel and hence go through a narrow band parallel sub channels. Okay? So we can view that alright, we have made our time domain signal, but actually that time domain is actually composed of each time is composed of narrow band parallel sub channels. Okay? So that is why it is called the famous orthogonal frequency division. So I know this is Azan and we should have finished here. So because, you know, the lecture was missed And last time, you know, I had an interconnection. I actually gave a message, you know, to making some connections at 12 o'clock that my internet is not working. But actually, I put that message in some other that there will be no quiz and this problem. And I was sorry, I couldn't inform you that the lecture could not be conducted. I should have put in that your section, but you know, there are 3-4 sections I put in some other section. That is why it is called the famous orthogonal frequency division multiple axis. FTID can be implemented with fast Fourier transform once NC is power of 2. Now, what is OFDM block length? Now, we have a problem here. We are not utilizing our resource because cyclic prefix is taking time. It is also taking a part. So the size of L and C plus L this time is being wasted. Similarly, this much average power is also being wasted. So what do? We already said, all right, we make very large blocks. All right, no problem. Achha, but he also says here that the total length NC, we cannot make it very large because this is also constrained by the time varying channel. Because you know, you increase NC, okay, and let us say it becomes so large that it becomes greater than the coherence time. Then you cannot use that NC because NC has to be less than TC or the coherence time. This is what he is saying. You know, under respect, TC is always greater than TD as we learn milliseconds and microseconds. But here we have to remember that yes, NC can be larger than this L in number of delay paths because it's very small, but it has to be less than, yes, it has to be larger than this because you know L has to be smaller than NC. So NC has to be larger than that, but it has to be smaller than TCW. You can see I have done this. NC has to be less than coherence, but it has to be greater than delay spread. It has to be in between. Yeah. So the channel is almost variant if it is less than, but it is greater so that there is no ISI. Yes. All right, so there will be a small portion, only L minus 1 symbols will have ISI, other symbols will have not ISI because so this is so large, the delay spread is very small, so only up to L minus 1 symbols, hence it won't be repeated. Same thing he has also tried to make us understand by the help of frequency domain understanding. So he says, all right, you know, all right, at W is the allocated bandwidth, right? So you have NC carriers, right? So you know every data symbol was put on those NC carriers. So the spacing between the carriers is W over NC, all right. But you know droplet spread, you know, roughly in chapter 2 is 1 over or something inverse of TC, 2 or TC, or let us say 4 TC. No problem if you put any constant. So what we want, we need the spacing to be much greater than droplet spread because you know droplet spread will change the frequency. Even if you have a narrow band signal or a simple carrier, droplet spread introduces some spread. Yeah. So you know the spacing has to be much larger than the spread because even if the signal is spread, it must not interfere with the next carrier. So this spacing must be much larger than the droplet spread. Other words, W is much larger than you know DS. DS is equal to 1 over 4 TC. So the NC goes there. NC over 4 TC, or you know 4 is just a constant. W has to be much greater than NC over TC. So you can see what you can see. You can take TC here. So TCW has to be much larger than NC. In other words, NC has to be much larger than TCW. Same thing that we saw here. NC has to be less than TCW. So NC must be constrained by TC coherence time. This is must. so that our in LTI system can work. So all that power is, so some researchers, they tried that already. We don't send this cyclic, okay, we can save power, but you know that induced a lot of harmonics, and so it became more difficult. So Cellwave is also used for timing and frequency acquisition in wireless applications. So it is normally not replaced. Now, how can I get frequency diversity? So, so let us say I have a narrowband channel, right? In 3.145. You can see this equation. 3.145. So here you can see that yes, I know this is N0. This is corresponding to the first carrier. N1 second carrier up till NC carriers. Every carrier is, you know, independent. All right, no problem. Yes, I agree. This is non-overlapping. Now for this model, yes, for this model, non-overlapping narrowband channel representation of ISI channel in 3.15 is non-overlapping. All the H were, all the D's, they were independent now. All right, and they were narrowband because very small, just simple carriers. All right, just taking a symbol. Now we know that those symbols must be independent because they are non-overlapping. Okay. The correlation between the frequency channel combination depends on the coherence bandwidth of the channel. So, but they might be correlated, and this is driven by the famous thing, which is bandwidth inversely proportional to the delay spread, you know, TD. So now we know that coherence bandwidth would over TD, right? But what is TD? Coherence bandwidth is 1/2 TD. But what is TD? We have learned many times TD is actually L over W, because L is equal to TDW. All right. I remember in passband signals, W is, you know, when you take baseband to pass a single carrier representation, W is baseband signal. But for these, you know, multi-carrier systems, especially OFDM, which is 100% multi-carrier, okay. So there, you know, W is the overall voltage, overall bandwidth of the wideband. Still be L over W. W goes here. This is W over 2L. So how many carriers will be highly correlated? So, you know, coherence bandwidth, this is the frequency where they're highly correlated. I divide this by the spacing between each carrier, you know. Every carrier has to be separated by this many spacing, W over NC. So I put the value of WC is W over 2 and W cancels. So I will get NC, and this NC is subscript. So I will get, sorry, no problem. This will be giving me NC over 2L. So these amount of carriers, they will be lying within the coherence bandwidth. So they will be highly correlated. All right. Other than those, they will not be highly correlated. NC over TL. All right. So what we can do? So we will do same thing as we do in time domain, you know, 3.2 section interleaving. One symbol. All right, send the second symbol in the second coherence time. Third replica of the first repetition coding, all right, in the third coherence time. So both three of them, one symbol repeated 3 times, coming in 3 coherence, you will get diversity gain of 3. So how can we exploit the frequency diversity? So we use this interleaving approach across the subcarriers. All right. So what I do, I place one symbol in one carrier. All right. I can place repetition of my symbol. All right. across a different carrier. So both those will go. All right, and those two will be received. But those two will be coming to two different channels, two different HFNs, and I will get my double sequence. In 3.2 section, where these H or these L were on different coherent time. Now they are in different carriers. Yes. Channel coefficient must be independent. So this must be made sure that the other carrier is more than the coherence bandwidth away from the first carrier. Then you can apply. There you are applying coherence time. You are applying here coherence bandwidth. This is the difference. All the things are repetition. So you can get an L-fold diversity gain. See? Depending on how many L's you use, how many carriers you use. All right, you can get this gain. So that it is called frequency diversity. It is not called time diversity because here you are using the coherence bandwidth constant. So these things you can do yourself. So we can go to the next section. Impact of channel uncertainty. So we try to cover, I think, 25 minutes. 25 plus 25 minutes. 75 minutes will be covered. 715 plus 25 will come out to be 735. 715, 725, 735, 740. All right, 740. This means we have covered our extra 25 minutes. All right, so that in this way, 3 lectures, this will be finished. Because I do not know whether this Wednesday class will be conducted before the Eid. It might be, there might be holiday announced. So we have to be made sure that we can cover that. Now this is the last section of this chapter. Now in the previous section, you could see we were doing coherent modulation, coherent combining, and we know H. All these H's were actually known. That is why we were multiplying, H with H. All right, so you get H mod squared or whatever you have seen many times. But how can we know H? Especially in fast varying channels, it is not easy to estimate H, especially, H cos and sine magnitude phases because they change at a fast speed. So we have to understand the estimation error. Remember the difference between detection and estimation as you are now becoming communication engineers. So you have to understand, especially at master's level, that what is the difference between detection and estimation. Remember what was detection? We studied in detail detection, and now in the next chapter we'll go for estimation. As now, because this section cannot be covered without not covering estimation theory. We have to cover some part of it so that we can understand its application or its implication. I want to do the system, but this section is not covered until we don't do estimation errors. So I will see. I can go quickly, but at this point we'll be stuck in the mathematics of estimation as you are stuck in the mathematics of detection. So there is a difference between estimation and detection. In detection, you are just detecting. Haji, plus 1 was sent or minus 1 was sent. Haji, XA was sent or XB was sent. XA vector was sent or XB vector was sent, or XB vector was sent. You were actually all determining which was sent. You're trying to detect which was sent. In estimation, you're actually estimating what is the actual value. You're not detecting, you're estimating. So we have to understand what is estimation in detail before we can be qualified to be called an engineer, and especially a communication engineer in these scenarios. Because remember, they will work in all wireless communications. It's the most difficult channel. Once you understand this channel, all the other channels are actually easier version of this wireless channel. So now what is non-coherent detection? We saw in chapter 3, section 3.1. In non-coherent, you do not know H. You have to apply a scheme so that you can use it without knowing your H conjugate. So we saw in section 3.1 one thing that was non-coherent. us do it further and compare coherent and non-coherent. So there you can see the figure, the difference was small, but we have to see what happens to the small distance as L increases. So answer depends on the prefix in the scenario. So we focus on the situation where channel uncertainty has the most impact. So we focus on DS spread spectrum. We focus on DS spread spectrum with frequency diversity. All right. So they are the most important. They are the systems which have the most significant effect of channel estimation. So we take the Rayleigh receiver example. So section 3.4.3 just as a revision so that you can understand this difficult section along with the relevant estimation theory. So I will the lecture will go up to 7:35. At 7:35 I'll take the attendance. So the lecture will end at inshallah 7:40. If you have any questions you can ask. Okay. So you know what was happening here. So actually what was happening, you could see this was a channel, this was a noise added, and then you were at the receiver, you have to multiply with the pseudo noise sequence. The pseudo noise sequence will, will actually convert it to baseband in a way, and then you multiply with this H conjugate, this estimate. This was coherent demodulation. This was what was actually happening. Or you could also say that signal is something like this, where X was the shifted versions of X. Then I multiply this Y with these, each of these L's. So I will get L different statistics. All right, so we will get L different outputs. This was we done. So let us go here. So there we have just now. So we have seen here in section 3.1 that if you have, for example, non-coherent detection, then you cannot use, because you do not know H, you cannot directly apply detection because you do not know H of X plus W noise. H, you do not know how it will change. You cannot use antipodal and binary, PPS cannot be used. So here we consider, binary orthogonal modulation. So we have XA and XB, they are orthogonal. These signals, they are, they are actually the extra pseudo noise se hua XA ban gaya, and you know that they are actually orthogonal. Okay? These pseudo noise sequences, they are actually orthogonal. Two different sequences, they are always orthogonal. And yes, their magnitude are equal, right? And also the shifted versions of XA, they will also be orthogonal. Nearly orthogonal. So we say they are exactly orthogonal, almost orthogonal, exactly orthogonal. So both for XA and their shifted versions are also orthogonal. That versions of the two sequences with different shifts are also yes. So if XA, XB are orthogonal, and their shifts are orthogonal within themselves, so then their convolution with the different shifts or with same shift but different symbols, this will be 0. Here is specifically written that L is not equal to L, so their shifts are not same. So this is more of he has put another condition, but this was not necessary. Because if XA is different to XB and you are saying they are orthogonal, you are saying they are orthogonal. then I don't know, even changing the shifts, they will still be orthogonal. So let us but follow the book, all right, no problem. So we say they are orthogonal, but their different versions of L are also orthogonal, specified, meaning that we are not saying that L the shifts are also different and X axis are also different. All right, in this way they will be definitely orthogonal, no problem. So we have, we multiply pseudo noise. I have told you to make these X. Selected code word of an orthogonal code by a common pseudo noise sequence. All right. So pseudo noise is always there. This depends. I think he should have this XA. I think should have already been spreaded. Because you are applying this pseudo noise property, this XA is already spreaded. Okay? Pseudo noise is all right. Now remember, in this section, we do not know what is H, but we have this Y, same Y that we got there in this section. Oh, sorry. Here you go. This Y, remember, X was 1 plus 2. This X was huge. One shift, then X, other shift, third, fourth shift. All right. So multiplying with HL, then adding. This was a huge. This was a single a vector. Okay. We have seen the length of n plus n. This was vector. So this will be Y. This matrix. This vector. So we projected this Y there only on on XX mod. Here we will be projecting it over XA and XB. So there we will receiving L. Here we will be receiving 2L. Sufficient statistics. So you can remember here we had XA and XB, they were just antipodal, they were just negative. So before, because we had done our this was the signal. So we were doing with this. All right. You can also see, I actually it is not explained here in proper way, but you can see my notes. There I told you how was this being multiplied there. So there you can do mod. So there you were getting L, but now you are getting 2L. Here you are getting only L because you were projecting this to L vectors. You will getting L different statistics, but here you will be getting 2L because here you will not be projecting it towards UL, but you will be projecting towards UA and UB. All right, both of them. That is why you will be getting 2L, not only L. कहाँ चला गया? Yes. All right. So you are getting 2L. Now the noises again will be noises here, no problem. They will be same as in the previous cases that we have learned. They are seen in the last chapter. So we have 2L different statistics. All right. And I can write this as if this output could be XA 0 or it could be 0 XB. Remember that for this we got U mod, so which will be XA, but here this is being done with XA. This will be giving me this LN different statistics. So there you can see the nodes you are getting UU mod, but here you will be getting XA mod and XB mod. So how can we decide whether XA was sent or XB was sent? So you will have these statistics, you will sum these up. What are these statistics are what? They are actually the auto, or you can say dot product of the Y received signal with XA and XB. So whichever value, this is just correlation. So we will just sum these sum of these squares, and whichever is greater than, we will say that XA was sent. If this is greater than XB was sent. Now, so we want to go to the mathematics of this, and he says that its error probability comes out to be like this. It is an exercise problem. So same format in 3.2 section, but mu here is different. So if I compare this with coherent detection of binary orthogonal modulation, so it comes out to be again 3. Remember 3.1 is very important because it comes even for rake receiver with coherent modulation, it was 3.125, and previously for repetition code it was only 3.12. 3.12 is repeating many times, but mu is changing here. So you're saying that if I just do anti-portal over this, so in that case I will get U as follows, rather than this I will get this. Now we can compare the performance of our non-coherent errors with the coherent one. So you can see here, this dotted line is for non-coherent, this is for coherent. So for small values of L, you can see they are almost same. But as L increases, you can see here you are getting L diversity gain, and that is why the error is decreasing like this. But here you are not getting this diversity gain. And you can see that that error is actually increasing for non-coherent. It decreases initially, but then it starts increasing. Similarly, here you can see another example, it decreases but it starts increasing, while for a coherent it starts decreasing. So it has been proven beyond doubt that for our system approach, coherent detection should be the norm. In fact, he says that if your L part tends to infinity, error probability for non-coherent go up to half the bits will be in error. It's very large error probability. So that is why Talon estimation is very important. We should know what is the value of H. Alright. And almost all wideband systems, they use coherent. You can see from 3G to 4G, coherent. Again, for rake receivers, this is the most difficult and also the most important. We will see that, and then we can understand also the others implications. So how this is used in industry? Actually, these two sections are 3.4, 3.1. They are more towards multi-user phenomena. So next time I will put this in the CLO of multi-user, because all things. The time is up, 7:36. I'm sorry, I've taken 1 minute more. So here I will stop the lecture. So we have covered up till this lecture. So industrial application of channel estimation we will go, which is still being used in 4G and 5G also the same thing. We will be studying from after this paragraph. So I will end the lecture, but I will first take your attendances.
सर क्विज कब होगा?
If you have any question, good idea. हाँ जी, आप लोग बता दें, फिर ले लें, फिर इंशाल्लाह कल ले लें आपका, मतलब कल, आई एम सॉरी, ऑन वेडनेसडे, इफ एवरीवन एग्रीज। हाँ जी,
सर नेक्स्ट मंडे ले लें सर, नेक्स्ट मंडे ले लें।
हाँ हाँ जी, एनी अदर, because I know some students will want to conduct on this Wednesday, so I want to take the opinion for everyone. जिन्होंने
सर
कहा
मंडे
नेक्स्ट
ही
मंडे,
करते हैं।
अच्छा 2 बंदे मंडे के, वो वेरी गुड। हाँ जी, इज,
नेक्स्ट मंडे सर।
अच्छा माशाल्लाह, 3 persons। हाँ जी, ऑल द अदर स्टूडेंट्स डू यू
सर
वांट टू?
वेडनेसडे को अंटेना की असाइनमेंट भी है, तो मंडे।
अच्छा 4 हो गए। हाँ जी, anyone student who differentiates with this opinion, because almost half the class says that Monday, but if still someone wants to say, he can. Only 7 attendees. Oh, yes. Anyone
डिसाइड
else?
तो हो गया है 4 के ऊपर। अब आधी क्लास मंडे को ही कह रही है तो मंडे को कर लेते हैं।
अच्छा, आप तो 5वें भी हो गए ना फिर। हाँ, अपने आप का ही फैसला बता दें, कोई बात नहीं। अगर आप अगेंस्ट हैं तो कोई बात नहीं, हर बंदे का अपना ओपिनियन हो सकता है।
सर वैसे मंडे को मेरी कुछ और कमिटमेंट है, मे भी शायद मैं अवेलेबल ना हो सकूं। सर मैं आपसे फिर डिस्कस कर लूंगा।
अच्छा अच्छा। हाँ जी, बाकी लोग बताएं, बाकी 2 लोग रह गए, वो क्या कहते हैं?
सर मंडे ठीक है।
अच्छा, और जो बाकी एक बंदा रह गया, जो भी रह गया, कौन रह गया?
सर उसका मैसेज आया है कि मंडे कह रहा है।
कौन? नहीं नहीं नहीं, जो अभी था, अभी जो अटेंडेंट है उसको छोड़े, जो नहीं चले गए। अभी जो अटेंडेंट में, अच्छा 7 लोग हैं ना, 4 वो हो गए, नहीं एक बंदा है जिसने भी नहीं बोला, अपना ओपिनियन नहीं दिया। हाँ जी, which student has not given his opinion?
सर मंडे को
बोलते हैं।
ठीक है।
अच्छा मंडे को, अच्छा मंडे को आपकी प्रॉब्लम। तो सलमान साहब, आप फिर आप मंडे को अगर नहीं है तो आप अपने नेक्स्ट से नेक्स्ट वेडनेसडे क्लास होती कि नहीं होती, ये भी तो प्रॉब्लम है ना।
सर असल में मैंने संडे को जाना है इस्लामाबाद, तो मंडे की शाम में शायद शायद मुझे यकीन नहीं है कि मैं अवेलेबल हो सकूं क्लास में, लेकिन काफ़ी चांस है मैं अवेलेबल होऊंगा। जस्ट सर एक मैं आपसे फिर डिस्कस कर लूंगा। आप मेरा या पहले ले लें, सैटरडे को ले लें, या फिर संडे को ले लें, ये हो सकता है।
ये तो सारों का ना ले ले संडे को, ये क्या ख्याल है? हाँ जी, नहीं यार,
बहुत
संडे को
जबरदस्त ख्याल है सर। संडे की सुबह में अगर ले लें तो अच्छा हो जाएगा, इजी हो जाएगा।
अच्छा, वो यार संडे को मसले मसाइल बड़े ना, वो घर भी तो होता है ना, घर के काम, वो बड़े हर के लिए मुश्किल हो जाएगा। हाँ जी, संडे सही है आप लोगों के लिए?
तो फिर अगर सर वेडनेसडे को ना हुआ तो छुट्टी हो तो हम खुद ही लेक्चर वो सिर्फ क्विज ले लेंगे, अगर लेक्चर ना भी हुआ तो।
अच्छा, ये आप कह रहे हैं, आप कह रहे हैं कि हम लेक्चर नहीं लेते तो हम कम से कम क्विज ले लें उस दिन, ये आप आइडिया दे रहे हैं?
जी सर।
वेडनेसडे को कर लें।
सर ये मैं उमेर के साथ हूँ, वैसे ये अच्छा आइडिया। अगर वेडनेसडे वाले दिन क्लास नहीं होती ऑफ होने की वजह से, तो हम क्विज तो कर सकते हैं ऑब्वियसली, 15-20 मिनट या आधे घंटे का, जैसे आप टाइम डिसाइड करें।
अब नहीं, वेडनेसडे का मुझे ये लगेगा वो बकरे चक्रे के चक्कर में ना हम फंसे ना हो, वैसे ये मुझे एक डर लगा हुआ। वैसे इंशाल्लाह आई थिंक कोई प्रॉब्लम तो नहीं होनी चाहिए। ठीक है, फिर वेडनेसडे तक फिर डिले कर देते हैं, सही, ताकि सबको फ़ायदा है ना। जिनका मंडे है वो भी फ़ायदे में होंगे, जिनके मंडे की प्रॉब्लम है वो भी फ़ायदे में हो जाएंगे, आपको टाइम भी मिल जाएगा। तो अब वेडनेसडे को देखें, अगर खुदा ना खाता, मतलब वैसे ऐसे नहीं कहते, अगर यूनिवर्सिटी ने छुट्टी कर भी दी तो फिर भी आपका 6 बजे क्विज होगा, और वो मैं फिर टाइम आपको मंडे को बता दूंगा कि मैंने वो, अगर मुझे जाना पड़ा मंडी वगैरह तो वो फिर मैं आपसे एडजस्ट कर लूँगा। तो मंडे को हम ये भी कर सकते हैं कि टाइम को शिफ्ट भी कर सकते हैं कि 6 बजे के बाद कर लें, या जो भी हम सेट कर लेंगे
ठीक है
आपस में
सर, सब
मगरिब के
फारिग ही
बाद।
होंगे।
हाँ, वो आधा घंटा ही है, तो ऐसा कुछ मसला तो नहीं होना चाहिए इंशाल्लाह। ठीक है, चलें ठीक है, मैं जल्दी से आपकी अटेंडेंस ले लूँ, काफ़ी देर लग गई। आज तो हमने जितना टाइम कवर किया ये सारा काउंट करें ना फिर, तो ये तो हम अपना नेक्स्ट टाइम इतना हमें एक्स्ट्रा नहीं करना पड़ेगा। कि जब लेक्चर एंड होगा तो आपने देखना आज हमने कितना एक्स्ट्रा टाइम दिया, तो हमारा लेक्चर भी तो उतना बड़ा हो गया ना, इसका मतलब। ऑलराइट, वायरलेस कम्युनिकेशन, एडिट। So today is 20th. All right. 1955 is present. 1835 present. 1836, 37, 39, 42. No one is present. Oh no.
Present, sir.
Oh, 42.
Yes, sir. Ghulam Mustafa.
All right. Take care. 1862.
जी सर
63.
प्रेजेंट
62 is present. All right. 1863. Absent. 41.
Present.
40, oh, sorry. 42.
Present.
43.
Present, sir.
44. 43 is present.
Yes, sir. 43 present.
43. Acha, 46.
Yes, sir. Present.
1, 2, 3, 4, 5, 6. Wait. So how can there be 8 students? There are only 7 attendees. कितनी हैं? हाँ जी. Who is this 8 one?
सर वो आपने 35
Now
लगता है
there are
गलती
only
से लगा
7.
दिया 2018 35.
Oh, sorry. Thank you very much. All right. Thank you. So I know the time. It is 7:43. This means how much time we have studied now? 15, 25, 35. All right. Takriban 45. So we have studied 30 minutes. All right. 28 minutes. So we can, the next lectures will not be this much large. All right. Thank you very much.